So we'll get started, and before we launch back into the lecture, I'd just like to make a few notes. So first is about the homework. Remember, the homework assignment consists of a worksheet as well as some problems from the textbook. And that's generally how things will go. I'll usually kind of split the homework between a worksheet that I distribute to you and things straight out of the textbook. The worksheet, as you might have noticed, doesn't have a lot of space to actually write anything on. So just think of the worksheet as the problem statement. That's not really where I would suggest that you work the problems out on. So instead, just fill out all the problems on blank paper, turn it in as one thing. And you will be turning in physical copies of the homework too. That's another thing just to keep in mind. Now that we're completely in person, there's not going to be any kind of submission through Canvas. So I don't know how you guys feel about that. Did you think it was kind of inconvenient or annoying to have to take pictures of stuff and upload it? Okay, so if that's the case, you don't have to do that anymore. Just turn in a physical copy. So any questions on that?
We don't have a class on Monday, right?
Yeah, thanks. That was the other thing I was trying to think of what the other thing I needed to announce was, and that was it. So, correct. Monday is a holiday, so we're not going to have any class on Monday. No lecture and no lab on Monday of next week. Okay? And because of the fact that we all break into 3 groups to do the lab, that means next week we'll just have no lab, period, regardless of what section you're in. And that's because I don't want there to be a lab that the Wednesday and Friday section do, but the Monday section doesn't do, right? So on weeks like this, we'll just have no lab. So the only thing going on next week is we meet for lecture on Wednesday, okay? So it'll be kind of an abbreviated week. And again, that's when you will turn in your first assignment as a hard copy. Right?
Wednesday, right?
Yeah, Wednesday. And again, you can see the assignment, the worksheets, and links to the textbook on the Canvas website, okay? So you should be able to find everything there. Is anyone having trouble finding stuff on Canvas? Let me know if that's the case. So with that said, let's get back into the lecture. Remember, this lecture is all about an introduction to electrostatics. And the first part of this that we did on Monday really touched on the conceptual stuff. So basically, we can understand a whole lot of different phenomena, like charging by conduction, charging by induction, just based on the fact that, opposite charges attract each other and like charges repel each other. But we want to be a bit more specific than that. We want to put some numbers and quantify the amount of force that exists between 2 charged particles. And that's where Coulombs Law comes in. This is a law of nature. It's an equation that tells us how this force of electrical repulsion and attraction actually works, and how you can calculate an amount of force using that. So first, I'm going to tell you a little bit of the history, and in particular, an experiment that was done by this guy, Coulomb, who's a French physicist in the late 1700s, to figure out how this force actually works. So what is the underlying equation that describes it? And this is a really rough sketch of the setup. So basically, you have this container, which holds a ball, which is connected to a thin wire. And this wire can twist if the ball is attracted to something else or repelled from something else. The wire just can twist. And then we have another charged ball over here, which is just in a fixed position. It's not attached to the wire. And again, if let's say we have 2 positive charges, just as an example, there's going to be a force of attraction, right? What's that going to do? That's going to cause this wire to twist. Now, it turns out this type of device is called a torsion balance. You can actually use it to measure forces very precisely, because how much the wire twists tells you how much force is present. There's a direct relationship between the two. So in other words, Coulomb was able to measure the actual strength of this force just based on the twisting of this wire in this apparatus. And so he was able to see what does the force depend on, how strong is it in different circumstances, okay? And so just as another historical note, there was a very similar experiment you might have learned about if you took 44 or 45. performed by Henry Cavendish to study the force of gravity. Because just like if we have two positive charges, right, if we just have two massive objects, they'll attract via the force of gravity, right? And you can measure the force of gravity using a really similar setup. And that was in fact done to see how gravity works. So let's discuss what Coulomb actually found out. What did he learn by doing these experiments? Well, basically it can be summarized in 2 points. The first point is that the force between the spheres is directly proportional to the charge on each one of those spheres. So let me give you an example. If we had one sphere and we doubled the amount of charge on it, then the force would double. It stands to reason that more charge, more force, right? But let's say we double the charge on both of the spheres at the same time, not just one of them. In that case, the force would go up by a factor of 4. So that's telling us that the charge on each one of the spheres is influencing the amount of force. Not just one of them, both charges matter. That makes sense, right? The other thing has to do with distance. So the second thing that Coulomb noticed is that the force between the spheres follows what we call an inverse square law. So just by a show of hands, if you've taken physics up until this point, you may have encountered the idea of an inverse square law. Is this ringing a bell to anybody? Maybe a few people? Okay, the idea is this. The force is inversely proportional to the square of the distance between the two charges. Okay, so let me give an example of that. Let's say we took the distance between the two charges and we cut it in half, okay? Because we have a smaller distance now, we have a larger force. That's how an inverse square law works. But it's not going to go up by a factor of 2, it's going to go up by a factor of 4, because it depends on the square of the distance, okay? So if we want to summarize all of this into sort of an equation, let's do it this way. The force between two charges, F, is directly proportional to, that's what this symbol means, Q1 times Q2, that's just the product of the two charges, divided by r squared. And there's our inverse square law when we have r squared in the denominator. Okay? So again, just note that as r gets bigger, r is the separation between the charges. When they get further apart, the force gets smaller. And when r gets bigger, the charges get closer together, and the force gets bigger. That's pretty much what we'd expect, right? If they're closer together, there's a stronger force. All right. So those are the basic points. Any questions so far? Okay. So let's try to turn this into a more solid equation that we can actually use to calculate something. So remember, if the force is directly proportional to Q1 times Q2 divided by r squared, there is a constant that has to appear out front. You guys remember this? If one thing is proportional to another thing, you just have to multiply by some constant to get between the two quantities, right? There's a constant of proportionality out front. And in our equation, that's K, all right? So K just represents the constant that sits out front in this equation. So to summarize, the electric force is given by K times Q1 times Q2 divided by r squared, where r is the distance between our two charges. Q1 and Q2 are the magnitudes of the two charges, so just how much charge is present in each one of those objects. And K is a constant, and I'm just going to give you the value of it, okay? K is equal to 8.99 times 10 to the 9, and the units are a little weird, but I'm going to show you how they work out. Newtons times meters squared divided by coulombs squared. Okay, so we have a constant out front times the two charges multiplied by each other divided by r squared. I should let you know that there's another way this is commonly written. Okay, so sometimes instead of putting K as our constant out front, notice we can write it as Q1, Q2 divided by 4 pi epsilon naught r squared. Now this may seem like a weird way to write the equation. Why do I need this 4 pi factor? We're going to understand that as the semester goes on. So for now, let me just tell you that These are two ways that the equation is commonly written. And basically, you can use the constant k out front or the constant 4 pi epsilon naught. Okay, it's the same equation, it's just a matter of like which way do we want to write the constant out front. So in other words, what I'm telling you is this epsilon naught guy in this equation is 1 over 4 pi k. So it's the same equation, just a different way of writing the constant. Can actually, someone who has a calculator handy, can you just do this real quick? Type in 1 divided by 4 pi times this number k. What do you get? Yeah, so epsilon naught, this constant, is equal to 8.85 times 10 to the minus 12. And because like epsilon naught and k are sort of inverses of each other, the units just get flipped. So it's Coulombs squared divided by Newtons times meters squared. And the last thing I'd like to point out about this is that Coulombs Law, which again describes how two electrical charges can either be attracted to each other or repel each other, and what amount of force is involved in that, is really similar to how gravity works. Okay, so I want you to think back to maybe physics 44 or 45, where you will have seen this before. Does this equation look kind of familiar if you squint at it a little bit? Okay, so this says the force of gravity between two masses, m1 and m2, is equal to some constant g out in the front times m1 times m2 divided by r squared. So if you just see these equations side by side, you notice they look very similar, right? There's a constant in front. Instead of two charges, we have two masses. But then it's an inverse square law, 1 over r squared. And the value of g is given here, but that's not really important. I just want to show the comparison, okay? So do we have any questions so far? Go ahead.
Yes, Professor. Let's say for the maybe on the test, can we use the value of k 9 instead of 9.99?
I'm sorry, can you say that one more time?
Yeah, can we use the value of k equal 9 instead of 8.99?
Yeah, if you're not doing a very precise calculation, that can be fine. A lot of times in the textbook you'll see that because it's so close to 9. Yeah. Okay. Anything else? All right. I want to say a little bit more about Coulombs Law. Remember, the equation that I just showed you strictly tells you what the magnitude of the force is. Okay? Remember, force is a vector. What does every vector have? It has two parts to it, right? Magnitude and direction. So this is really important to remember. The equation I showed you is fine for determining the magnitude of the force, but to determine the direction, you need some additional information, okay? And basically, how do we determine the direction? Like charges, what do? Positive and positive. They repel, right? Opposite charges, what do? That alone is enough to know what the direction is, okay? So we know the direction based on the fact that opposite charges attract and like charges repel. And we know the magnitude because we have Coulombs law, which we can use to make the calculation, okay? So basically, with those two pieces in place, you can calculate the force in any situation, okay? But I'll show you a few examples, right? We have opposite charges on the top. So charge 1 is the one on the left side. Charge 2 is the one on the right side. That's how I'm labeling things in this picture. So in the first picture on the top, we have a positive charge for number 1 and a negative charge for number 2. And they're going to be attracted. So there are actually two forces involved, right? Force is a two-way street, as we know from Newton's third law of motion. Okay, if I've got charge 1 attracting charge 2 is also attracting charge 1. Those things are happening at the same time. In other words, those forces are equal and opposite. Remember that, Newton's third law? All forces come in equal and opposite pairs. So if we want to show that they're attracted, we'll have the two force vectors going towards each other. That's what it means to be pulled together to be attracted. Okay? And let me just note how I'm doing the notation here. Okay? So in the first picture where you see F21, that means the force that charge 2 is exerting on charge 1. And guess what? It's going to the right because it's an attractive force. And then over here we have F12. That's the force that charge 1 is exerting on charge 2. And it's attractive, so it's going to the left. Okay? Now, in either case, if we have positive, positive, or negative, negative, it's repulsive. So what we're going to do is show the two forces going away from each other. So does this basic picture make sense? And again, Coulombs law that describes this force of either attraction or repulsion, it's in accordance with Newton's third law, which says those forces are equal and opposite. Right? You see that? There's the same amount of force here, but the force vectors are pointing in opposite direction. There's the same amount of force here, but the force vectors are pointing in opposite directions. So that's completely in line with Newton's third law. All right, good on that? So let's take a bit of a break then to do a problem. What I want you to consider here is the interaction between two electrons. Okay, I have an electron here, and I have another electron here, and they're some distance apart. Okay? Now, there are two things that could be happening. And of course, we have electrical forces, right? The two electrons, since they have the same charge, are going to repel. But two electrons technically have a gravitational attraction to each other also. Anytime you have two massive objects, they do interact through gravity, even if the gravity is really weak. So what I want you to try to do is find the ratio of this electric force that we just learned about to the gravitational force, which is over here. And all the different numbers you're going to need, value of this constant K, the value of this constant G, the mass of an electron, the charge of an electron, it's all given here. So you should be able to just do the calculation. And the takeaway point, if I could just spoil it, is that gravity is very, very weak compared to the electric force. The electric force is much, much stronger. So this ratio is crazy big. So try it out, see if you can find out what that ratio of the two forces is, and then we'll go through that together. And as always, just try to talk to the person next to you about how to tackle this one. Like you're pretty close to the end. stamping pen? All right. Some people may be still working on this, and that's fine. Just want to make sure we're moving along at the right pace, so we'll go through it together. Switch over to the document cam. Okay, so just a few things to remember. The force of electrical repulsion between the two electrons, which I'll call an Fe, is given by Coulombs Law. So remember that's K, Q1, Q2, divided by R squared. Or if I want, I can write this as K, Q1, Q2, times R to the minus 2 power, right? And in a similar way with the force of gravity, Fg, what I have is capital G, M1, M2, divided by R squared. And again, I can write that as capital G, M1, M2, times R to the minus 2 power, like this. So what I'm interested in is what is the ratio of Fe over Fg? Because again, the electrons will repel each other through this force, but they'll attract each other through the force of gravity. So I just want to compare them. I want to know which one is bigger. And so to put in what we have K, Q1, Q2, times R to the minus 2 power, divided by G, M1, M2, times R to the minus 2 power. Notice I can cancel the distance. So the answer does not depend on the distance. So the ratio of the forces is going to be the same regardless of how far apart the two electrons are. Okay? And at this point, we can realize that, well, it's two electrons, so they have the same exact charge, don't they? What do we call that elementary charge? What variable do we get for that? We use a lowercase e for the elementary charge that you'd find on an electron. So if we have two of those, that's e squared, okay? And then we have big G, and then they're both electrons, so we just use the mass of an electron and square that. So basically, we want to calculate this quantity right here, okay? And in the interest of saving time, I'm going to leave out the units, but rest assured they cancel out to give you just a ratio with no units. Remember, our value of K is 8.99 times 10 to the 9. Actually, I take it back. I'm going to put the units in. The units are newtons, meters squared, divided by coulombs squared. Okay, what is the elementary charge? 1.602, 10 to the minus 19 coulombs, and we're going to square that guy, right? Big G, that's 6.67, 10 to the minus 11. Units on this guy are newtons, meters squared divided by kilograms squared. And then we'll multiply that by 9.11 times 10 to the minus 31 kilograms. That's the mass of an electron, and we'll square that. So when you punch all these numbers in to your calculator, what comes out?
So 4.17 times 10 to the 42.
Oh, that should say 42, 10 to the 42. That's right. Okay, so in other words, the electrical force is like 10 to the 42 power times as big as the gravitational force. So that's just completely, overwhelmingly larger than the gravitational force, okay? So the lesson is, if we're doing a problem where maybe there's an electrical force between some particles, let's say electrons or protons, don't worry about gravity. It's so small, it's not important, right? The electrical force completely overwhelms it. Now with that said, why is it that, I don't know, gravity seems to be the dominant force if I drop this pen? Why is the electrical force not a factor here in the pen falling to the ground?
Oh, because M is so much bigger than any electrical force acting on the pen.
Okay, but the thing to remember is, in most cases, when we're just dealing with ordinary matter, it's electrically neutral. So in other words, like the Earth itself doesn't have like a net charge to it, because it has just about as many protons as it has electrons.
That's what we saw in the lab.
Yeah.
We need those extra.
Right. So again, the point of this problem is just to say electrical forces are much stronger than gravitational forces in general. Okay, so let's go back to the slides and let's do an example. And this one is more of an intense calculation. You're going to see a lot of problems like this on the homework, but hopefully if you see just a few examples of how to do this, you'll be able to do any example you encounter. So here's what's going on. We have 3 point charges that lie in the XY plane, as we see here. And what we want to do is calculate the total force acting on charge number 3 due to the other 2 charges. All right, so first of all, let's just think in terms of the qualitative picture. How should we attack this? So how many different forces are going to be acting on charge number 3 up here? 2 forces, right? For one, it's going to feel a force from charge number 2. What type of force will that be? That will be repulsive, because charge 3 is positive, and so is charge 2. So there's going to be a repulsion away from charge 2. Okay? What's the other force? Yeah, so charge 1 is going to be attracting charge 3. So if we think about, just in a hand-wavy way, how the forces are going, there's one force going straight up, right? And there's another force going diagonally like this. And what we have to do is add them together. Now, forces are vectors, right? When we add them together, we have to account for that fact. So I hope you guys remember how adding vectors works from your previous physics. So we're going to put kind of all these ideas together. So we'll start by copying down the picture. All right, so I'm going to be using a coordinate system where this is kind of important to keep track of coordinates, where this is my y-axis going like this, straight up, and then this is my x-axis going to the right like this. So remember, we have charge Q3 up here on the y-axis, and I'm going to show that as a positive charge. We have charge Q2 down here. Let's put that right at the origin, how about? And that's a positive charge as well. And then we have charge Q1 down here on the x-axis, and that's a negative charge. So that's basically the picture. Okay? Now, I'm just going to label some distances we're given. We're given that this is 30 centimeters. So the distance between Q2 and Q3, just given, is 30 centimeters. And the distance between these two is 52 centimeters. So that's what we know to start off. And we also have the values of Q1, Q2, and Q3, the actual charges. So next thing I'm going to do is draw sort of a force diagram where right here where Q3 is located, I'm going to show the force vectors that are acting on it. So remember, as we just established, it's going to be feeling a force going straight up like this. It's a repulsive force away from charge 2. So I'm going to call this force F that 2 exerts on 3. F2, 3 is how I'll write that out, okay? And then, as we said before, there's an attractive force. And I'm going to draw a little dashed line just so I get the direction of this force correct as I draw it. Attractive force towards charge number 1. So there's my force vector. And the way I'm going to write this is F1, 3. So those are my 2 forces. Now what we're going to do is calculate the sum of those 2 forces. Okay? So before we actually get into that, remember, Coulombs Law says the force of electrical repulsion or attraction, the magnitude of it, is given by the equation Fe equals K Q divided by R squared. So Q is just the 2 different charges we have, okay? So for 2 and 3, the distance between them, r, is this distance along the y-axis. That's our 30 centimeters. So I'm going to call this R23. Cool? The distance between 1 and 3, which I need for this force between charge 1 and 3, is the diagonal you see here, okay? So I'm going to call that R13. And we don't immediately know that, but how can I calculate this distance? Just, it's the Pythagorean theorem, right? So it's going to be square root 30 squared plus 52 squared, which is equal to, someone just give me the number for that.
60.03.
Okay, 60.03, and technically we're keeping 3 sig figs on that, okay? So 60.03 centimeters is that distance. All right, now the next thing I'm going to do is break one of these vectors up into components, okay? So for F23, this is pretty straightforward. It only has a y component. I hope that's clear to see, right? But the other force, F13, has both an x and a y component. And as you know, when you add vectors together, the standard way to do this is to break each one into components and then do the addition. So I'm going to show you what the components are right here. So this component that goes along the y-axis, that's F13y. It's the y component of that guy, right? And then I'm just going to have to kind of point to it because I ran out of space. This is F13x. Is that clear? And what am I going to need to know to calculate those components? I'm going to need to know some kind of angle, if you recall. So I'm going to label this angle right here, theta. And also, just for reference, that same angle theta can be found down here. So that's going to be useful that these are the same angle theta. Okay? So we good so far on the setup? All right, so next, we want to know the total force acting on charge number 3. And that's a vector, which is the sum of F13 plus F23. We're going to add those vectors together. But, like I said, we can break each one into components, so that's what we're going to do next. So let's start with F13. That's the one that has both x and y components. So as far as the x component of this guy is concerned, is that a positive x component or a negative x component? Positive. It's going along the positive x-axis. So I'll just make a note of that. And then how do I take a force where I know the magnitude of it and the direction of it, and get the x component out? How's that going to work?
You multiply by cosine theta?
Yeah, so if I take F13, the magnitude of that guy, and then I multiply by cosine of the angle theta, that's the x component of this force, okay? And remember, cosine goes with the adjacent side of your triangle. So that's how you can tell, okay? Cosine goes with adjacent. And I'm going to put an I hat to denote that I'm talking about the x component. Okay. Then, check out the y component. Is that going to have a positive sign or a negative sign?
Negative.
It's negative. So here's how I'm handling this. There's different ways to approach this. This is what I suggest you do. I'm going to just put that negative sign in at the start, and I've already accounted for it, so I don't have a minus sign hanging out anywhere else, okay? So I have F13 magnitude. What do I multiply by to get this y component? Multiply by sine. Remember, sine goes with the opposite side, so if you look at this triangle, this is the opposite side, okay? And then I have a j hat, unit vector. So that's the first F13 force vector broken into components, okay? Now the second one, fortunately, is really simple. What is the x component of F23 up here? There's no x component. There's no part of this that lies on the x-axis. So just, I'll write 0 I hat, and then what do I do next? Yeah, if if you have a vector like this, where there's only one component that's not 0, that component is just the magnitude of the vector. Does that make sense? This says magnitude F23 multiplying j hat. All right, so now we've got that set up. Good. So what I'm going to do next, and this is very common, is I'm going to collect the x components together, and I'm going to collect the y components together as well, okay? So for the overall x component, for the total x component, I've got this plus this. So I've got magnitude F13 cosine theta I hat. So that's my F total x component right there, okay? For my F total y component, I have to add these two pieces together. That's going to be magnitude F23 minus magnitude F13 sine of the angle theta. That's my F total y component. Okay? And now we can directly calculate these things. Okay? Because remember, anytime I need a magnitude, I'm going to use Coulombs Law up here, right? And then the last thing we need to do is just figure out what cosine and sine are. Okay? Any ideas for that? Like in other words, I want to plug in a number for cosine of theta, sine theta. How should I do that?
Well, we have to figure out the theta, which is simple because it's a 90-degree angle and the other two could only be 45.
So it doesn't mean they have to each be 45 though, because these distances are not equal.
You just set it up.
Use arctangent with adjacent with opposite adjacent 31 to 2.
So I could do that. In other words, I could look at this triangle right here, where I know all these different distances, and just calculate theta. I could figure out how many degrees it is, right?
Yeah.
But I don't even have to do that. Remember, I don't need to know what theta is. I just need to know what cosine theta is.
So cosine is adjacent over hypotenuse.
Yeah, that's probably just a more straightforward way to do it, right? Cosine of theta is the adjacent side, which is this, divided by the hypotenuse, which is that. So I can just take the ratio of those two, and that's my cosine theta. And then similarly with sine, that's opposite over hypotenuse. So I can just directly calculate that as well. Okay. So for my F total x component, I have the magnitude of the force between 1 and 3, which is given by Coulombs law as K, 8.99, 10 to the 9. The units here are newtons meters squared per coulomb squared. That's K. And then since I'm talking about 1 and 3, these two here, I need to just put the two charges in. So I'm just going to directly grab what was given in the problem. So for charge number 1, we had 86 microcoulombs. So that's 86 times 10 to the minus 6 coulombs. Now I want to just note something here. That's actually negative, right? But I've already accounted for the direction, so I'm not plugging in a negative value here. That's going to give me the wrong answer, okay? Now, then we have Q3, which in the problem is 65 microcoulombs, so that's 65 times 10 to the minus 6 coulombs. And then we're going to divide by r squared, so the distance between 1 and 3, which is 60.03 centimeters. I better put that in meters though, right? So how would I put 60 centimeters in units of meters? Yeah, I'll just put it this way: 60 times 10 to the minus 2 meters, and then we have to square that distance. So what have I done? I've calculated the magnitude of F13, but I need a cosine theta in there as well, right? So cosine theta, what did we say it was? Let's just do it real quick as scratch word. Cosine theta is adjacent divided by hypotenuse, isn't it? So that's 52 divided by 60. So I'm just going to put that right in for cosine theta. 52 divided by 60. And that's my total force in the x direction. So you can punch this into your calculator, it's kind of a long calculation. If you do that, you're gonna get 120.8 newtons. So you can follow along, just verify you get 120.8 newtons. We're keeping 3 sig figs on that, okay?
Q3 and Q1 were given to us, right?
Yeah, in the problem, all the charges were given. So when I'm plugging these in, it's just giving values, okay? Okay, so we got that under our belts. Now let's do F total Y. So remember, that's magnitude F23 minus magnitude F13 times sine of theta. So I'm going to do that whole thing. All right, magnitude F23, that's given by Coulombs Law, just like all of these. So it's K, which is 8.99, 10 to the 9. I'm going to leave off the units here to save a little time. Times the product of the two charges, which are 2 and 3. So the product of these two charges, which given in the problem are 50 microcoulombs, or 50 times 10 to the minus 6 for Q2, and 65 microcoulombs, 65 times 10 to the minus 6 for Q3 up here. And then, of course, I have to divide by R squared. What am I putting in for this R value?
0.3 meters.
Yeah, so I'm interested in the distance between 2 and 3, right? So I better be putting in this R value, which is 30.0, 10 to the minus 2, because we have centimeters. We want to convert that to meters and square it. Okay? Okay, so that's F23 magnitude right there. Then I'm going to subtract F13 magnitude, which is the same thing we had up here, remember? So I'm just going to copy those numbers down. 8.99, 10 to the 9, times 86.0, 10 to the minus 6, times 65.0, 10 to the minus 6, divided by 60.03, 10 to the minus 2, square that. But then we need to multiply by the sine theta, okay? So sine theta is opposite over hypotenuse. So that's going to be 30 over 60, basically. Okay, now again, this is a lot to punch into your calculator, but when you do it, you are going to get, and you can verify this, 254.9 newtons. Okay? Oh, you can't see that? I'm sorry. Yeah. Yeah, you're going to have to remind me of that a lot because I don't see what's on the screen from over here. Okay, so a lot was going on there, right? But hopefully you see how we got to this point. Any questions so far? We're going to do a few other things before we finish this problem. Basically what we found is what is the x component of the total force, what is the y component. What we want to do next is find the magnitude of this total force and the direction. So this is telling us overall how much force is acting on charge 3 and in what direction is it being pulled. That's what we're going to get by finding the magnitude and direction. So just how do we do that? If we have an x and y component, how do we find the magnitude?
You square both of them and then add them together and then square root.
Yeah, so it's Pythagorean theorem once again, right? So here, let me just kind of sketch this out, right? Our total force, by the way, points something like this into the first quadrant because its x component and its y component both came out positive, right? And so what we found is F total x, this part, and F total y, this part. We know those. And I'm just going to indicate a little angle theta here. Okay, so the magnitude of F total is equal to the square root of F total x, square that, plus F total y, square that as well. So basically just plug these two into the formula and tell me what you get.
282.9.
All right, so you get 282 newtons. Basically, if you plug this in for the y component and this in for the x component. And then how am I going to find the direction? If I know the x and y components of the force, how do I find its angle? In other words? Yeah, I can use the tangent function, right? How is tangent defined again? Opposite over adjacent. So again, if we look at this triangle here, what's my opposite side?
Y.
It's my y component, f total y. And then my adjacent side is f total x. So in other words, if I want the angle of my force relative to the x-axis, inverse tangent of f total y divided by f total x. And again, we know what those are, so just plug them right in and tell me what you get.
$64.6.
64.6 degrees. So, therefore, this charge Q3 is feeling a total force of 282 newtons at an, yep. That total force is 282 newtons at an angle of 64.6 degrees. That's what we found. All right? So any questions on this example?
Can I see the screen where the question was real quick? I didn't finish the other.
Yeah, let's go back to that. This one?
Yeah.
So yeah, I showed you all the Q values here and all the distances we need here.
I have a question here. Let's say if you give the same distance and change the side of the charge, do we have the same result?
No, you wouldn't have the same result because then the force would flip around and you'd have to, in the way they would add together would change. Yeah. Go ahead.
Wouldn't the direction be negative 60? Does that mean that it's being attracted that way rather than down towards number one?
So the way those two forces add together just happens to point this way.
Oh,
Yeah. Yeah. You have to add them together to get that result. Okay. Anything else? Okay, so again, that might have been kind of a long one, but it's important to know how to do problems like that. And it really combines a lot of ideas that you've seen previously, particularly dealing with vectors. Now here's a simpler one because it's one-dimensional. You don't need to break stuff into vectors like before, okay? And this one I want you guys to try out. So we have three charges, point charges on a line. We have Q1 here, Q2, Q3. And you can see what the values of those charges are, okay? The distances are also given. So my question for you is, what is the total force acting on charge number 2, the one in the middle, due to the other two? And again, let's just start with the qualitative picture. Charge number 2. In what direction is charge 3 exerting a force on charge number 2? Yeah, so charge 3 is attracting it, so there's a force to the right. What about charge 1? Pulling it to the left. So it's basically being pulled in two different directions. As you're going to find, it's not getting pulled equally strong in both directions, so there's still going to be some overall force you're left with. They won't cancel. But what I want you to do is try to see what that comes out to when you add those two forces, pulling in opposite directions to each other. So try it out. Maybe take about 5 minutes and see if you can do this. Yes. So just the way I'm color coding this on this problem, I think everyone might want to hear this. I'm showing negative charges in red, positive charges in blue. So that's just the way I'm showing
Doesn't
it.
have to do with the electrons.
Yeah, there's nothing special about those colors, just personal choice.
Find the total force.
Yeah,
Is the magnitude and direction?
yep, of the total force. And then the direction is either going to be positive X or negative X. That's really your only two options. Oh, okay.
In the last example, like, when we were dealing with the X side, we need 8, even though this was negative.
Because this is just a magnitude. We've already accounted for the direction.
Alright, so like, when we were dealing with 2 or 3, the magnitude would be positive.
Yeah. Yeah, so it's just like before. Once you've got the direction, you don't need to account for that anymore. So in other words, but we're gonna go through this. Okay, so again, some of you may be still working on this one, and that's fine. Does anyone have an answer? Did anyone get it?
I got 0.30 newtons in the positive X direction.
Perfect, that's right. So let's go through that real quick. So like I said, this is a slightly more simple example because everything's just in one dimension. We don't have to do so much work to break the vectors up, right? So here, I've got Q1, which is negative, sitting here. And then I have Q2, which is, yeah, actually, I'm getting a lot of glare. I'm going to pull this down. Yeah, Q2, which is positive, sitting right here. And then I have, again, Q3, which is negative, sitting at the far right-hand line. Okay, so I have some distances. This is 30 meters right here, or sorry, 0.3 meters right here. And this is 0.2 meters right here. All right, so let's just do a force diagram like before, showing all the forces acting on charge 2. Like we said, it's getting pulled this way, attracted towards charge 3. So the way I'm going to label that force is F32. That is the force that 3 is exerting on 2. And then being pulled the other way is I'm going to call this F12 because it's the force that 1 is exerting on 2. Okay? That's the picture. And let's just call the X direction to the right. So anything that's going to the right is the positive X direction. Anything going to the left is the negative X direction. That's how we'll do it. So basically, my total force, it's only going to have an X component, so that's all I care about. It's going to be the magnitude of F32 minus the magnitude of F12. Does that make sense? If I just take the strength of this force, subtract off the strength of that force, I get the total. Because everything lies in a line, and the two forces are going in opposite directions. Okay? If they were going in the same direction, I would add them, but they're not. Okay. So for each force, we're going to use K, Q divided by R squared. So let's start with F32, how about? K is 8.99 times 10, that's not 10, 10 to the 9 newtons times meters squared per coulomb squared. And then we have the two charges, which are 3 and 2. What is each charge? Can you remind me what's charge number 3?
-4 microcoulombs.
Yeah, that's -4 microcoulombs. However, I'm just interested in the magnitude here, right? So I'm going to plug that in as a positive value. I've already accounted for the direction. So this is 4 times 10 to the -6 coulombs for that. And then for charge 2, what do we have? We have 3 microcoulombs. So 3 times 10 to the -6. And then I have to divide by the distance between 3 and 2. What's the distance between 3 and 2? That's my 0.2 meters, isn't it? And I should square it, I should say. Okay, then subtract off the force between 1 and 2, which is K, 8.99, 10 to the 9 newtons meters squared per coulomb squared. What is charge number 1? What is the value? 8 microcoulombs. It's a negative charge, but again, this is the magnitude, so any signs we're leaving out because we're just getting the magnitude. And then times charge 2, which is 3 microcoulombs. And what is the distance between those two charges?
0.3.
That's our 0.3 meter distance, and we square that. And yeah, if you do this, you're going to get something positive. So when you subtract the 2, you'll still end up with a positive result. And it's about 0.3 newtons. You can verify that on your calculator. What is the fact that this came out positive telling us? Yeah, it's being pulled in the positive x direction, which is to the right. So 0.3 newtons to the right is the answer here. Are we all good on this?
Does that have to do with the distance being less?
It has, so it's a combination of things. Yeah, that could be part of it. Yeah, that's basically it, because the charge is more, but the distance is less. So the distance is more, so it's a smaller force. This is a smaller force than this. Yeah.
So just to be clear, the only reason you put positive and negative signs on the charges is to show which ones are attractive and
Yeah, I do this up here. So let me just kind of recap the process. At first, I just want an accurate force diagram telling me what direction the forces are going in, okay? And once I've established that, it's pretty clear how they add together, right? Now, at this stage, we're just plugging in magnitudes. In other words, I just need to know the strength of this force minus the strength of this force. So because we're talking magnitudes, magnitudes, remember, are just positive numbers, right? That's why we do that. Anything else? So in other words, you'd be sort of double counting if you inserted a negative sign. All right. So that's the way I approach this. I think it's the easiest way to keep track of directions. If you have to plug in the negative numbers at this stage, it gets kind of confusing. Okay. So yeah, that's that, and we'll keep it moving. So we've spent about an hour talking about Coulombs Law, which describes the electric force between two charges. Pretty much the rest of this lecture, which we're going to stay on like into week 3, basically, it's going to go pretty long, has to do with this idea of an electric field, okay? And this concept is super, super important. It's going to come up throughout the semester, and then later on, we're going to see a slightly different manifestation of this called the magnetic field. So the idea of a field is something I really want you guys to understand after this lecture. So let's get into it. Now, if you've taken Calculus 3, just by a show of hands, have you taken Calculus 3? Okay, so I'm going to teach this assuming you haven't taken Calculus 3, because that's not a requirement. but if you have taken Calculus 3, some of this is going to look familiar, okay? So let's talk about the idea of a vector field. Okay, a vector field is a function that assigns a vector for every single point in space. That may sound a little abstract, but just take a look at the picture and it'll give you an idea, right? Don't even worry about what this picture is showing us. It's just clear that it's a vector field because if you notice, every single point along the picture, there is a vector, right? Every point in space gets a little vector. So if you just imagine some space filled with little arrows, which have magnitudes and directions, that's a vector field, basically. Okay, so every point in space gets a vector. And this is really useful in electricity and magnetism, as we'll see in this class. But also, vector fields are used in other areas of physics. For example, you can use a vector field to describe how a fluid is moving. Let's think about how that would work just as an example, right? So let's say this picture is showing us water flowing, okay? Each vector might describe how fast the water is flowing at that point and in what direction the water is flowing at that point. So this would be showing us the water is kind of going up at this point, but then it's looping back around and going down as we get to this side. That's the idea of a vector field. Okay? Every point in space gets a vector. That's useful in different ways. So the electric field is an example of a vector field. It's like a special case of a vector field. And this idea was first developed by someone named Michael Faraday, and we're going to see more of his work throughout the class. So this is how it's defined, okay? It's going to seem a little abstract at first, but hopefully after you see this, and then some examples, you'll understand. So the value of the electric field at any point in space is given by this. It's a pretty simple equation. It's just E equals F divided by Q. So E is a vector, right? Better be a vector. That's a force divided by a charge. Think about it as a force per unit of charge. But let's kind of get into the details of what that is actually saying to us, okay? This is saying if I take what's called a test particle, imagine I just take a positive charge and I just put it somewhere in space. Just put it at some point. If there are other charges around, it might be feeling a force, right? My test particle might be feeling a force. So if I take that force and I divide by the electric charge of my test particle, that gives me the electric field. So again, may seem a little abstract, but once I show you the example on the next slide, hopefully it'll make some sense. Before we get to that though, let's just do a quick note on units, right? If I have a force divided by a charge, what's my unit of force? Newtons. What's my unit of charge? Coulombs. So just note that electric fields have units of newtons per coulomb, because again, it's a force per unit of charge. Okay? So, with that said, let me show you just the simplest possible example, okay? Remember, the electric field is F divided by Q. So, what I want to show you here are two pictures showing us the electric field that is created by a positive charge and the electric field that's created by a negative charge. And it's pretty straightforward to see why the electric fields look the way they do, okay? So imagine this charge is just sitting here. It's already in place, right? Then I'm going to imagine I take my so-called test particle, right? Imagine I have another charge, a positive charge, that I just put somewhere in the vicinity of this guy, okay? So I'm going to ask you a few questions. If I take my positive test particle and I put it right here, what direction is it feeling a force? So in other words, this charge is already in place, right? It's a positive charge. If I put another positive charge right here, what direction is the force? It's being repelled away, right? Okay, if I take that same test particle, put it right here, it's being pushed away, it's being repelled. If I put it over here, it's being pushed away. So in other words, The electric field created by a positive charge is just going out in all directions. And the reason for that is if you put another test charge nearby it, it would just be pushed out whichever way you put it. And in a similar way, let's think about the electric field created by a negative charge. Okay? So a negative charge. So I'm going to take my test particle, positive charge test particle, and just put it, let's say, right here. Which way is the force acting on it? Yeah, so if I have a positive charge and I put it right here, it's going to be attracted. So it's going to the right. What if I put it right here? Up. And then if I put it right here? It's just attracting, right? So in other words, these vectors are showing me that they're going away from a positive charge and they're going towards a negative charge. Okay? So do you see why that would be the case? So all that is to say, if I take that force and I divide by the charge of my test particle that I put in the vicinity of these guys, then I get the electric field. That's how we define the electric field. Okay? So that way of defining it may seem a little abstract, as I said. So we're going to get to some concrete equations that we can use once we have this definition. All right. So again, right now what we're doing is we're saying, what is the electric field created by a single point charge? Okay? So it's not like a charge that's spread out over some big area. It's just a point charge. So think, an electron or a proton, something like that, right? So this is the notation we're going to use, okay? Capital Q, that's going to be my so-called source charge. That's the charge that's creating our electric field. That's the charge that's responsible for creating the electric field. And when I write little q, that's going to be our test charge that we imagine putting somewhere nearby, okay? We clear on that? So this is the source, and then we have a test charge little q that we'll just imagine putting somewhere nearby. Okay, so let's introduce that test charge into our picture. There it is. So I have big Q, little q now, right? There's a distance between them, right? Let's call that r. So the force that's acting on my test particle, as we said before, is going to be repulsive. It's going to be repelled away from big Q. So I'm going to show the force going to the right like this. And, well, what is that force? It's given by Coulombs Law, right? We already know that Coulombs Law describes the force that this charge is going to be feeling. It's given by K, big Q, little q, divided by r squared. And then to show the direction, I'm just going to write r hat. We all familiar with this kind of notation? This is a unit vector just showing me which way the force is going. Which way is it going? It's going in the direction of r, basically. Okay, it's going radially out. Okay, so next, what's the definition of the electric field? The definition of the electric field is, it's that force acting on our test particle divided by the charge of our test particle. So, in other words, I'm just dividing out little q. That's all I'm doing. What happens when I divide out little q?
We're not performing the force of the force charge.
Yeah, so basically you're just going to get rid of this term right here when you divide out little q. And so let's show that. We get k, big Q, divided by r squared in the r hat direction. So this is a formula. This is really important formula that shows you what the electric field due to a point charge actually is. You can calculate now what the electric field from a point charge is using this equation. Okay? So let's kind of summarize everything we learned about the electric field from a point charge so far. The magnitude of the electric field is given by K times big Q. That's whatever the charge creating our electric field is. divided by r squared. That's how we calculate the magnitude. How do we know the direction? We already went through this, right? The direction is it's going to point away from any kind of positive charge. So if you have a positive charge, the electric field is just going out. And if you have a negative charge, it's coming in. It's going towards negative charges. And as long as we have these facts established, we can calculate basically any electric field. Okay, so just to let you know how that's going to go. If we have more than one point charge, we can just add all of the individual electric fields together to get the total electric field. So at first, it's going to look like those last couple of examples we've been doing. But then, starting next week, we're going to see how to do this with integration by doing it with calculus methods. Okay? All right. So after this, we're going to go into some examples of just how do we calculate an electric field due to a bunch of charges. But before we get into those examples, I just want to emphasize why we're doing this in the first place. Like, why we already have this force thing, so why do we need this additional electric field thing to complicate our understanding? Well, the electric field is actually really useful because basically it allows you to describe the effect that some charged particle has on the whole space around it. This is how you really should be thinking about it. You have an electric charge just sitting there, but it fills all the space around it with this thing called the electric field. We can visualize that electric field, again, using these vectors going out away from the charge, or if it's negative, in towards the charge. And every single charge in the universe is a source creating some kind of electric field. That's how you want to think about it. So then, once we know what the electric field is, we might just have one charge, we might have a whole bunch of charges creating an electric field. But once we know what that electric field is, we can then say what will happen if you put something in that electric field. Okay? In other words, if I know what the electric field is, and I imagine placing some charged particle in that electric field, I know how much force is going to be exerted on it. Because remember, we said it before that E is F divided by Q. Just flip that around to say F is equal to Q times E. So if I put a charge Q in an electric field E, its force is Q times E. That's simple. Okay? So that's the reason this is useful, at least in terms of problem solving. But I also want to say that electric fields are real. They're not just some math trick that we're doing to solve problems. In fact, electric fields and magnetic fields, for that matter, which you'll learn about later, this is how charged particles interact with each other in our universe. If there's no electric field, basically nothing about electricity and magnetism, as we understand it, could really work. And we might get to this towards the end of class, but what is light, the light that you're seeing with your eyes right now? As it turns out, it's nothing but electric and magnetic fields oscillating. So hopefully we'll get to that at the very end of the semester. So the point is, it's a useful concept to do calculations, but beyond that, it's a very real phenomenon. Okay. So the last thing that we'll talk about in this lecture today is the electric field due to a collection of point charges. So if we have any number of point charges just lying around, how do I calculate the total electric field due to all of those point charges? That's the question. So the answer is pretty straightforward. The way electric fields work is they follow what's called the principle of superposition. And that's really just a fancy way of saying that you can add electric fields together. So in other words, if I have Q1, Q2, and Q3, and let's just say Q1 and Q2 are positive, Q3 is negative, just as an example. If I want to know what the total electric field from these charges is, all I would do is add each individual electric field to the next one until I've covered all of them. So in this example, the total electric field, let's say at this point right here, let's say that's the place we want to calculate the electric field. It's just the sum of E1 plus E2 plus E3. And the way that we're going to calculate that sum, again, is using vectors, because this is a vector thing. So if I have charge Q1 and it's positive, remember, electric fields go away from positive charges. So my E1 is going to be pointing to the right, just away from this charge, okay? My E2 is also going to be pointing away from this charge. But since Q3 is negative, E3 is going to be going towards that charge. And so once we see how the vectors look, we can add them up. We can calculate that sum. So in general, if we have 3 or however many, just take the sum of each individual electric field vector until you've included all of the charges. So this is a summation showing us that we add up the electric fields from all the charges, and that gives us the total. Okay? So do we have any questions on that? So if we have a bunch of point charges, add their electric fields, you get the total. Okay, so pretty much the rest of the lecture is examples of doing that. Okay, this is going to be another long example. Just going to warn you in advance, okay? So get ready. Here's the situation. We have 3 point charges in the XY plane. We have Q1 located at the origin, and it's a negative charge minus 35 microcoulombs. Okay? We have Q2 located on the x-axis over here, 40 centimeters away from the origin. So the 40 centimeters is shown there. And its charge is minus 95 microcoulombs. Then on the y-axis, up 30 centimeters from the origin, we have this positive charge, Q3, which is 50 microcoulombs. So we're interested in what is the electric field at this point right here? What is the electric field created by these charges at this point, which is directly above Q2 and directly to the right of Q3? Okay? So there's a follow-up to this. We're going to calculate the total electric field. Then, once we've done that, the follow-up question is, imagine we placed a charge of 15 microcoulombs here. How much force would be acting on it? That's the follow-up. Okay, so let's start with this. I'm sitting here at point P. What does the electric field do to Q1? What direction is it pointing in? Yeah, so remember, Q1 is a negative charge. Negative charges create electric fields which go towards the charge. So I'll have an E1 vector pointing kind of like this. What about Q2? Which direction would its electric field be pointing? Straight down. Yeah? And then what about Q3? Straight to the right. So I have 3 vectors, and I have to add them all together. Okay, that's the idea. And now we have the equations we need to do that sort of addition. So just like before, I'm going to recreate the picture. I have x, my axis going like this, or what the hell am I saying? That's y. And then I have x going like this. Q1 is at the origin, that's a negative charge. Q2 is to the right of that, that's also a negative charge. And then Q3 is on the y-axis, that's a positive charge, right? And then the point that we want to calculate the field, I'll call that point P up here, is again just to the right of Q3, just above Q2. So it forms kind of a rectangle like this, okay? All right, so what are some of the distances? This distance on our rectangle is 40 centimeters. That's what we're given. This distance is 30 centimeters. And how about we show those forces now? Okay, So remember, E1, the electric field due to this charge, since it's negative, is pointing right towards it. So I'll just draw a little line like this that connects these two. And I'm going to show E1 going directly towards charge Q1 because it's negative. Okay, and then I'm going to have E2 going straight down, like we said, because it's going towards a negative charge. And then E3 is going straight to the right because it's going away from a positive charge. That's how this works, okay? So, out of all of these three vectors, like which one is kind of the most complicated to deal with? E1, right? That has x and y components. The other two just have an x component or just have a y component. So it's a little simpler. So since we know that eventually we're going to have to break up E1 into x and y components, let's just draw how that goes on the diagram. So here, this is the component E1y. That's the y component of this vector. This is the component E1x. And if I know this angle, I might be able to break that down into those components, okay? And just a helpful note, I see that same angle right over here. Okay. So, let's now look at some distances. So remember, r refers to the distance to a charge. So it's the distance between my point that I'm interested in and a charge. So for, let's say, charge 3, what is my distance? That's the 40 centimeter distance to get to charge 3. So I'll call that R3, how about? For my second charge, what's my distance? Yes, 30 centimeters to get to my second charge. So I'll call that R2. Then R1 is the long side, right? How are we going to get R1? Just another Pythagorean theorem, right? That's a right triangle. We have square root 30 squared plus 40 squared. And what does that equal to? 50. Yep, 50 on the dot centimeters. Okay, so we've got our work cut out for us. We good? Okay, so remember, I want to know the total electric field, which is the sum of all my individual electric fields, which are E1 plus E2 plus E3. And again, these are vectors. Got to treat them like vectors. So just like in the last example where we were dealing with vectors, I'm going to take each one and break it into its x and y components. So we'll start with E1. This vector is going like down and to the left, right? So what would the sign of my components be? Like the x component, what would the sign be? Positive or negative?
Negative.
Yeah, this is going on the negative x-axis. What about the sign of my y component? This is also negative. It's going down, right? So it's, in other words, this vector is in the third quadrant, so it's both got both got negative x and y components. Okay. So my x component is going to be minus magnitude E1, and then if I take the cosine of that angle theta, that'll give me my x component, and I'll put an I hat unit vector next to that. My y component, also negative, is going to be magnitude E1 sine of my angle theta. Put a j hat unit vector next to that. Okay, for E2, do we have an x component?
No.
It's pointing, yeah, it's not pointing at all along the x-axis, so it's got no x component. So I'll say 0 I hat, and then its y component, is it positive or negative?
Negative.
It's negative, so I'm just going to see I'm putting that sign explicitly in there. And then E2. And it's only pointing on the y-axis, so it's just the magnitude there, okay? Okay, next, E3. Does it have an x component? Yeah, in fact, it only has an x component. It has no y component. So this would be E3, the magnitude of that guy, times I hat plus 0 j hat, because it has no y component. And just like before, we're gonna sort of organize things here. So for my total x component, I have, let me write it out, the magnitude of E3 minus the magnitude of E1 times cosine of theta. So that's my total x component. For my total y component, I'm just adding these two. So I have minus E2 minus magnitude E1 sine theta, and then I'll have my j hat unit vector right there. So here's E total x component, here's E total y component. Okay? Good so far? So let me just show you the magnitude of an electric field is equal to K times Q divided by R squared. We derived that earlier. Okay? So basically, anytime I see a magnitude, I'm going to use this formula. But then we also have to work out our cosines and sines. Okay? So here, let's just do that. Cosine theta. What is that equal to, according to this diagram?
30 over 50.
Yeah, so here, in case there's a lot going on here, so let me just redo this. We have 50, okay, we have the angle theta here, and then we have 30 and 40. So if I want to know cosine of the angle theta, that would be 40 divided by 50, right? And if I wanted to know sine of the angle theta, what would that be? Yeah, it'd be opposite over hypotenuse 30 over 50. So that's how we're doing this, okay? So now let's calculate E total x. E total x is magnitude of E3. I'm going to leave off the units here just to save some time. But it's going to work out as newtons per coulomb, okay? It's K, which is 8.99, 10 to the 9. And then we need to know the charge 3, which is 50 microcoulombs from the problem. So 50 times 10 to the minus 6 for microcoulombs. And then we're going to divide by R for that third charge, which is 40 centimeters, or we could say 0.4 meters, and square that. So that's my magnitude E3 term. Then I have minus magnitude E1, which is K, once again, 8.99, 10 to the 9, times Q. My charge for the first guy is minus 35 microcoulombs. But remember, I've already accounted for the direction, so I'm just going to keep that as a positive value, which is 35, 10 to the minus 6 coulombs. And then divide by the distance here. That's our long distance of 50 centimeters, okay? So in meters, that's 0.5, and I square the distance, okay? But this also has a factor of cosine theta, which we said is 40 over 50. So again, there's kind of a lot there, but once you have it, we can calculate the total x component. And I'll just show you what it works out to. It's 1.80, 2 times 10 to the 6 newtons per coulomb. I'll keep 3 sig figs on that. Okay, for E total y. Again, we have the formula. We're just plugging in the values at this point, right? We have everything in place. So we have minus E2, okay, minus the magnitude of E2, which is K, once again, 8.99, 10 to the 9, times the actual value of that charge. For the second charge, we had minus 95 microcoulombs. We already got the sign out here, so I'll just plug in 95 microcoulombs, or 95 times 10 to the minus 6 coulombs, divided by the distance to charge 2. That's our 30 centimeter distance. Remember, that's right here. I want to put that in meters, so that's going to be 0.3, and I'm going to square that guy. Okay, then I have minus magnitude E1, which we wrote down over here, so I'm just going to copy that again. Minus 8.99, 10 to the 9, 35 microcoulombs, 35 10 to the minus 6, divided by 50 centimeters or 0.5 meters squared. And this guy picks up a factor of sine, right? That's 30 over 50. Okay, so if you work this out, here's what you get. You're going to get something negative, actually, minus 1.024 10 to the 7 newtons per coulomb. So just to be clear, what we have now are the x and y components of the electric field created by all of these three charges at this point in space. Okay. So if we want to get the magnitude of E total, I showed this before, right? If we have the x and y components of the vector, we can get the magnitude by taking the square root of the x component squared. Yeah. Oh yeah, sorry about that. I'm gonna have to get used to this. This is a little weird. Yeah, thanks. So can someone crunch this real quick? These are our x and y components. We're gonna use them to find the magnitude. So we're just plugging them right into here.
1.04 times 10 to the negative 7, I think.
Positive 7 on that one. Yeah. 1.04 10 to the 7 newtons per coulomb. So in other words, this is how strong the electric field is. That's what a magnitude is telling you. But if we wanted to know what direction the electric field was pointing in, this would be given by an angle theta, right? Yeah, and so we did this before, right? It's going to be the inverse tangent of the y component divided by the x component. Remember that? If we want to know the angle of a vector, we take the inverse tangent of the y component divided by the x component. And that will give us what now? Again, just plug in the x and y components that we found.
Negative 80 degrees.
Yeah, negative 80 degrees. And let's discuss what that means. So this electric field has a total x component which is positive, right? And a y component which is negative. So it's pointing something like this. It's a positive x component and a negative y component. So that angle is negative because it goes below the axis. If it went up above the axis, then it would come out positive.
What do we call the strength of the field?
The strength? We call that the magnitude. Yeah. Okay, so remember, what we've done so far is calculate the electric field, but what we want to do is do the follow-up question, which is, imagine I put a test charge at this point, how much force would it be feeling? That's the follow-up question, and we'll tackle that right now. All right, so here, E is the force that our test charge would feel divided by the actual test charge Q. And so if I rearrange this to solve for F, because what I want to know is a force at this point, that's going to be Q times E. So the magnitude of the force that's going to be felt by this test particle, if we put it at point P, on charge little q, is going to be this. We're just going to take the charge and multiply by the electric field. It's pretty simple, right? So our test charge we were imagining putting there is 15 microcoulombs, so 15 10 to the minus 6 coulombs. And if I multiply by the strength of our electric field, that's going to give me the strength of the force that it feels. Okay? So I'm going to take that, multiply by 1.04 10 to the 7 newtons per coulomb. And that will give me, will tell me what that gives us. (156 newtons). And the direction is minus 80 degrees, just like before. So, because the electric field is telling you what direction that force would be in. That's the whole point. So, if I were to take that charge and put it here, they'd be feeling 156 newtons of force at an angle of minus 80 degrees like this. Okay? By the way, I'm going to save these papers if you want to, like, I don't know, take pictures of these later or something. Okay, they'll be ready. Any questions on that example before we move on? We have about 15 minutes to go. I do want to use it because I want to get to some questions for you guys to work on, okay? All right, so I have two negatively charged particles. They have the same exact charge, actually. So it's just minus Q, same Q, right? And they lie along the line, as we see here. My question is, in what region, is it region 1, which is just off to the left? Is it region 2, which is right in between the two charges, or region 3? Which one of those regions do we have an E field going to 0? That's my question for you to answer. And, or is it nowhere, that in none of these regions the E field goes to 0? Okay? Now, if it's not obvious how to attack this, here's what I would suggest. Okay? Take each one of these regions and just draw the electric field due to both of the charges. And then do the same thing here, and do the same thing here. If you see that they could cancel out because they're going in different directions and with equal magnitude, then you could say the electric field goes to 0, right? But if I had two electric fields going this way, they don't cancel to give you 0, right? So just try to figure out where it could go to 0. Which one of those regions? And start by drawing those pictures. So see what you get. And talk about it with the people next to you. They'll help. All right, so we're going to put this one to a vote, and you have to vote, right? Mandatory. So who thinks it's in region 1 where this electric field's going to 0? Region 2? Looks like you get this. Good. Should we even continue voting? It's region 2, right? Okay, cool. I don't think we need to go through that if you all got it. So let's do another one. How about this? We have two particles with equal and opposite charges that lie along a line. Again, we have region 1, 2, and 3. So this one's negative, this one's positive. So try to figure out, using the same sort of strategy, where do we have the electric field going to 0? So again, just like before, in each region, draw a little picture showing your two electric fields. Try to figure out if you can cancel out.
I figured it's the distance are increasing if you were to go into then it would charge the positive charge particles by the negative would be lesser than the repulsion goes up into the blue. But I'm not sure. Because I'm not sure what the distance they do that. But I'm assuming because they are going to be doing it.
Yeah, so I guess the caveat should be the same thing. But it's we're not saying.
I'm pretty sure.
Yeah. All right, so let's put this one to a vote as well. And everyone, I just want to make a quick comment on this problem, right? Of course, if you're infinitely far away from a charge, then the E field can go to zero, right?
Well, technically, it will always be a minuscule value, isn't it?
It's an asymptote thing. So what I'm telling you is to not consider that. Consider some finite distance away, right? So what do we think? Is it region 1, 2, 3, or nowhere? Nowhere. So look, I know you guys have this, but I just want to show you the way I would sketch out these diagrams to get the answer. I think it might be useful. So in this problem, what we have are two charges. I'm calling them A and B. So A is what I'm going to call the negative charge on the left, and B is what I'm going to call the positive charge on the right. And then we have regions 1, 2, and 3, okay? And there's only a few things you need to remember, which is, that E points towards a negative charge, and it will point away from a positive charge, okay? So let's say we're over here in region 1. My electric field due to charge A, which way is it going?
To the right.
It's going to the right, it's going towards this negative charge. And I'm going to show that as kind of a big electric field because we're closer to charge A, right? What about charge B? This positive charge to the left, because the E field is going to point away from it. But we're a lot further away from that charge, so it's going to be a smaller E field, okay? So although the E fields are going in different directions, there's not going to be cancellation of them, right? Because one's bigger than the other. Okay. Now what about in the middle, in region 2? So for this negative charge, the E field goes towards it. So that's our EA. And for this positive charge, the E field goes away from it, which is in the same direction to the left. So it's EB. So definitely can't get cancellation in the middle because the E fields are going in the same direction, right? All right, now let's consider region 3. That's our final region to consider. The E field due to charge A, which way is that going? Yeah, it's a negative charge, so it's going towards it, which is to the left. And we're a bit further away now, so I'll show that as kind of a smaller vector. Because remember, the E field gets weaker with distance. There's EA. And then we have EB. Which way is that going? To the right. And it's going with a much bigger magnitude to the right, because we're much closer to that charge. So it's really the same argument as in region 1. You can't get the cancellation to happen. Okay? So that's why the answer is nowhere. We do have 5 minutes left, but I can't really think of a good way to use those 5 minutes. So we'll finish up here and pick up on Wednesday of next week where we left off in the lecture, okay? Just remember, next week, homework is due Wednesday. We have no class on Monday.